Today I'm going to talk about realizing large structures in space from a mechanical point of view. In science fiction movies, you see typically enormously large structure, much larger than in the International Space Station. But I'm going to concentrate more on unmanned spacecraft and why this is important. Since the dawn of the space age, the size of the payloads have continued to grow steadily, but the demand for larger space structure always outpace the availability here. So typically, what are the large space structures doing, the ones that I'm going to present? Typically, they're manipulating the electromagnetic spectrum in some way. Typically here we have so to do better science, we would need larger apertures, sort of larger size disks here, and also they are protected with sort of sunshades. In this way, we can increase the opportunities to see exoplanets by seeing stars, and we can also characterize those stars by having a broader electromagnetic spectrum here. For better communication and better sort of Earth imaging, we would need to have larger sized antennas. So better Earth imaging. We also have that the demand now today with handheld technology would require larger and larger sort of apertures to meet those demands. Sort of mobile phone, the data rates there. In the 1940s, there was an idea of having unlimited power from space by building very large space solar power satellites in this way, and then in a way beam down the energy on Earth. And those are sort of kilometer in size, so it's more sort of science fiction-like here. Solar propulsion would constitute an unlimited propulsion technology. This has been demonstrated with sort of smaller satellites, CubeSats, that Sven will talk about after this talk. But to reach reasonable acceleration values, you would need also sail sizes that are sort of sized almost like half a kilometer in size. So what are the challenges of realizing these structures? If you do a survey in the literature, you would see enormous amount of concepts that are available. Some are science fiction-like. Those are currently only available on paper. And those that have flown has been typically around 20 meters in size and are the most mechanical simplest structures and the most robust ones. We have sort of inflatable technology here. We have this kind of spring back antennas that sort of flips open by storing energy, and also some sort of mechanical structures here. So I've tried in this talk to sort of break down what the main challenges are to realize these larger structures, to do better science, to have better communication. So the first challenge would be that since the 1960s, the available space in the launch vehicles have not increased a lot in size. So typically what we have here in these rockets here that is lifting the structure from the surface of the Earth into an orbit is that it's around 5 meters in diameter that you can have there. This is what fits in the commercial sort of satellite, in the commercial launch vehicles that are available. But if we look at the sizes of the antennas that are up there and that are proposed to be up there, is that they are the sizes of the largest airplanes. So we need to find a way, like an umbrella, right, to squeeze it into a small volume when it's not being used, like sort of on a sunny day. And it should also be light, but then when they are operational, they should be at their full sort of potential, the full largest size. So this is the first challenge, but there are even greater challenges that we will see here. Is that the quality of the signals, all in the microwave spectrum and also in the visible spectrum, is not only dependent on the diameter of the sort of the mirror or the parabolic surface here. They're also depending on the surface precision. And the surface precision is not only, if you manufacture it, you need to manufacture it to a very high precision. And obviously, it's much larger to design a structure or to manufacture a structure which is highly precise but large in size. It's much easier to have a high precision structure which is much smaller in size. So that's one of the challenges here. And we can see here also now, here is the launch limit at around 5 meters. So we see that those antennas that are above the launch limit, those structures that are above the launch limit, they typically have a very low surface precision. This is 1 millimeter here. The ones that have very high surface precision here in terms of wavelength, they are closer to the launch limit. So they're not allowing so much sort of complicated unfolding techniques. We should keep this in mind. This is the sort of the diameter here, but we should also look sort of at the importance of the thickness here. So designing highly precise and large structures, that's the main challenge. If we go then and check that, so now there are some equations going on here. So there is a close relation between the precision we can have and the stiffness of the structure. So this is beyond when it has been manufactured, because when we launch it into space, it's going to be subjected to the space environment. The space environment typically have very low acceleration values in comparison with Earth, where we have sort of 1g. So here we have sort of 10 raised to minus 6 to 10 raised to minus 3 g's here. And here is the sort of the displacement, the surface precision that we're discussing. So this would be what we are discussing sort of in space here. So if we have a structure that has a very low thickness, it's typically very flexible and it has a very low first natural frequency when it sort of vibrates. And depending on that frequency and also the acceleration values that it will be subjected to when you have solar pressure, you have other types of sort of low drag pressure, which are this order of magnitude. If the structure is too weak here, so here we assume that it's a 10 hertz is the lowest eigenfrequency. This means that if within this region here, the structure itself can control the surface precision. If you have higher acceleration values here and you would require a higher surface precision, you would need to add the control system that compensates for these errors here. And the control system will add complexity and cost and it can also increase the risk. So this is one. So if we look at some of the designs here that are up in space, the Hubble Space Telescope, it has 100 hertz as the lowest natural frequency, and that can passively control the surface precision. If we look at the James Webb Space Telescope that is scheduled to be launched next year, which has sort of a 6 meter diameter aperture here, and then these sunshades to control the temperature. It has an order of magnitude lower eigenfrequency here. And already there, you would need to have some kind of control system to control the high precision of the surface. And then looking further to some of the sort of designs that are being proposed for even larger apertures, you push down the eigenfrequencies even here sort of below 1 hertz. So that means that you would need to have a control over the full loads that the telescope is going to be experienced. So that the subjected loads there. This adds the complexity and cost. The fourth challenge here is the astronomical cost of these missions here. So if we're using conventional technology, there has been sort of an empirical formula devised here, which says that the mission cost of future space telescopes. You can see here the James Webb Space Telescope. It's close to sort of $9 billion here. It depends on, as we said before, it's the diameter, how large is the mirror here, but it also depends on the wavelength, sort of inversely proportional to the wavelength. So smaller wavelength in the visible spectrum will increase the cost. And we also have that the operating temperature is also increasing the cost. This means that you would need to have these typically large sunshades to keep the temperature of this surface reasonably constant over the to not have any not have too large thermal distortions of the surface, which will decrease the surface precision. And if you extrapolate using this formula to sort of larger apertures here, you see the very high cost using the conventional technology. So this indicate that we need to have a shift in design from conventional technology to something else. Because if this has been developed now for 18 years almost, the James Webb Space Telescope, and if you extrapolate this, we're gonna have like almost 50 years to develop this one. So what have we done here at KTH in terms of research that have tried to push the advancement of large space structures? I mean, we have done a little here. So one of the interesting topics, concepts here is that we have flown a prototype of a space web, which is sort of a planar web here. The prototype that was flown was sort of 2 by 2 meters in size, so very small. And this was in collaboration with, it was financed by the European Space Agency, and it was done in collaboration with 2 universities in Glasgow, Strathclyde and the University of Glasgow here. And the idea with this space web would be that we deploy it with sort of centrifugal forces, so we wrap it around this hub here, and then we deploy it by rotating it, and then we had a reaction wheel sort of adding angular momentum from the hub out here, but sort of counter rotation. And this was done in the Rexus program, which is sort of a program where students can fly their experiments on a sounding rocket, reaching around 80 kilometers in altitude and giving a few minutes of weightlessness for the test. So here we see the rocket that is on its way to the launch. And as Mark said, this was also launched as Mark Balloons. This was launched from S-Range in Kiruna. So I wish that I could say that this experiment was a success, but the video footage from the experiments tell a different story here. So we see here that we see that a film showing how the deployment looked like. So there were cameras pointing radially out from the hub, trying to catch the 4 corners as we're deploying. This is a bit messy here, but what we can see here is that we see that the picture going back and forth in this way. This means that the central hub has changed the rotation direction. And one of the reasons that we have found by trying to reconstruct or reanalyze what was happening here in the deployment dynamics was that there was an error in the controller. I think this is the most likely. So the reaction wheel was rotating very fast. It didn't deploy, so it was reaching a speed when the corners were released, and then the speed was too high. We didn't have enough torque to control the deployment. Ending up with us. So here we could see, I hope you can see that this is 2 of the corners basically sitting together. So they have entangled in a very sort of strange way. But I think we learned a lot from this project. We have written sort of and published a lesson learned article about this, how not to do it. If someone is want to sort of take up this challenge, they should learn from our mistakes here. Another project that I've been involved with together, also sponsored by the European Space Agency, together with the university in Rome and also with a company in Italy, is a deployable ring structure that could be used for supporting a communication antenna surface here. And here we used a concept called tensegrity, which means that there is a lot of sort of flexible members, but very few stiff members. And the idea behind this was to have, if there's a lot of flexible members, then we can package into a very, very tight package. So here we can see the ring structure that is suspended from the ceiling with very long, thin sort of fishing lines, trying to have a simulated zero gravity system here. And this is being used when we try to simulate it. And we're going to see here now that here is a a video footage how it deploys. There is a large risk also in this project for entanglement, that some of the flexible members get caught on some of the stiff members. So this was a prototype that was being built here, that was around a few meters in diameter. And we actually got a patent on this one as well. But I can say also that the lowest natural frequency is quite low, so it doesn't sort of outperform current technologies here. So coming to the end of sort of the session, what is then the future of large space structure? As I said before, the very astronomical cost and also the complexity means that we need to do something else. We need to sort of move to a different type of technology, and there are some already ongoing developments around the world in this area. One idea could be that we use robotic assembly. So we use very small, high precision pieces that are built together, with building a large space structure with sort of robots. And there the challenge is, how do we, even if each of the piece is very precise, how do we control that the whole structure becomes sort of precise? That's one of the challenges here. Because you can cut 1 meter in length to precision maybe with plus minus 1 millimeter. This is what you can do in the workshop. The precision that is needed here is sort of 10,000 times more precise to get into these low values. Another idea is that we have these kind of similar structures. We have sort of the mirror, we have a sunshade, we have sort of the optics at the feed here. But we don't have any structure holding them together. We used sort of the control techniques and sort of formation flying, with sort of controlling the relative positions and also controlling the sort of the relative attitude here. We don't have any structure holding them together. But still there is a challenge of constructing the sunshade and this very large primary mirror, because they are still very large in size. Perhaps the most promising concept here would be to use additive manufacturing. And this has already been tested in space by some American companies, that we send up a 3D printer with some material, and then we can upload the drawing of the structure we want to construct, and then we construct it sort of on demand in space. So then we just need to refuel it with some more material if we run out of that sort of. And then the advantages with this one is that we don't have to I mean, the structure doesn't have to tolerate the loads that are here on ground. It's the light loads in space, so it can be made much thinner and much more economical. So this is one of the promising future, and both the European Space Agency, the EU, and also NASA are investing a lot of money in having in-space manufacturing to sort of have this paradigm shift. But I must also say that there are some dark clouds on the sky when it comes to large space structure here, is that this is called space debris. So if you launch a very large structure in space, is that a sitting duck for orbital debris? You will increase the risk of being hit by orbital debris if you are launching sort of, say for example, a solar power satellite in lower Earth orbit. What is the risk of this being hit by space debris? So I think with this kind of somewhat gloomy outlook on this area, I think I will end my talk here. Thank you very much.